Evidence A. What evidence have you discovered about temperature and energy?
Heat and temperature. These are two terms that people often think means the same thing, but they don't. It's important as physicists that we have these definitions correct. So, what is the difference? Let's look at the two items on screen now. On the left is a cup of coffee, and on the right is a lit match. It should be really obvious to you that the match is much hotter or at a higher temperature than the cup of coffee. But it's not so obvious that the cup of coffee actually contains much more heat. In order for us to see this clearly, let's zoom in and look at the particles inside. In the coffee, there's millions of particles, all moving fairly slowly. But heat's a measure of the total energy in a...
Okay, let's compare heat and temperature. You guys can take notes on paper. We'll have heat on one side, and temperature on the other side. We'll draw a line down the middle. We'll compare the two. And we've already learned that heat equals total energy.
System. So if we add up all the energy of every particle, we find there's loads of heat energy there. Now, if we look at the match, we see there's only a handful of particles, and although they're zipping around really, really quickly, because there's so few of them, if we add up the total energy here, we find it's much lower than in the coffee. Temperature, however, is a measure of the average energy.
So temperature is equal to the average energy of the system.
In a system. And as we can see in the match, the particles are moving much, much faster than in the coffee. So the average energy, and hence the temperature, is much higher. To recap, heat is the total energy in a system. And because it's energy, it's measured in the same units as energy, which is joules. Temperature, however,
we're going to write that as well. Measured in joules.
Is the average energy in a system. And there's loads of different units for temperature, such as Celsius, Fahrenheit, and Kelvin.
So we measure temperature, sometimes in Celsius, sometimes in Fahrenheit, and sometimes in Kelvin.
It's really important to make sure you remember and understand these basic definitions as we move through the rest of the heat topic.
Okay, so I'm going to do a little drawing. The coffee cup had more heat energy than the matchstick. And for temperature, The matchstick had more, or a higher temperature. And the coffee cup less. The coffee cup had more heat because it had more particles. Those are particles. And the matchstick had less heat because it had less particles. But temperature is more of a measure of how fast the particles are moving. So they were moving super fast in the matchstick and slower in the coffee cup. So therefore the matchstick had a higher temperature because it had faster atoms. Faster atoms equal higher energy, and the coffee cup opposite. So that is the difference between heat and temperature. Okay, evidence B for the energy CER Google form. We're going to look at a simulation of temperature and pressure. In this container is some neon atoms. Neon's an element. I'm going to put the temperature in Celsius. The temperature has to be pretty cold for neon to be a solid, and right now neon's a solid. The pressure's at 0.0 atmospheres. And what I'm going to do is show you what happens to pressure as you increase temperature. Watch the pressure gauge up above. It's going up, up. And as long as I keep applying heat, the pressure will increase. The pressure is increasing because the atoms of neon are moving faster. And as they move faster, they gain energy and they push harder against the container. That is what increases pressure. So for our notes, what we're going to do is we're going to write temperature and pressure is our title, and an increase in temperature equals an increase in pressure. And the reason for that is atoms move faster at sides of container harder. This is the pressure increase. And then we will draw a little picture to show that. There's our container. Here's our heat. And here's our atoms moving fast and bumping more often against the side of the container. Increase in temperature equals an increase in pressure. Okay, we're going to do evidence C. What evidence can we discover about speeding up condensation? We're going to watch the video, What Speeds Up Condensation?
Hi, I'm Robin Higgins, and this is What Speeds Up Condensation? So let's just remind ourselves what condensation is. Condensation is the movement of something from the gas form, and this is the best that I can draw a gas, to the liquid form.
All right, so we will draw that quick in our notes. This is our gas. And a gas to a liquid. That's horrible. That says liquid. That is what we call condensation. Gas to a liquid, condensation.
And so the most common example of this we see is usually if you have a cold beverage, you put it down, you're going to see water droplets on the outside of that beverage. And those water droplets, put our beverage here, actually came from the outside gas. So there was gas, water vapor floating around, and they found your glass, and then they condensated on the edge of it.
Okay, so you have a glass of cold beverage. And I want to write the word cold on here. And we're going to say that the outside temperature is warmer than the beverage. So the water vapor in the air is what condenses onto the cup. The cup is cold, a lower temperature. When the warmer air touches the outside colder cup, it goes from a gas to a liquid.
And so what speeds up this process? Well, remember that to move from a gas to a liquid, it needs to be a colder temperature, right? So if you have something that's a colder temperature, then it will make more condensation faster. And so that's pretty much the example we see here on Earth in our everyday lives.
All right, that's as much of the video as we need to watch. So in summary, how do you speed up condensation? Speed up condensation by decreasing temperature. Make things cold, speed up condensation. If you want a lot of condensation on your cup, make your cup really cold and make sure that the air around it is warmer than the beverage in the cup. And that is it for evidence C. Okay, next we're going to take notes on evidence D. What evidence can we discover about air pressure? We're going to watch the video, How Heavy is Air?
You may not realize it, but from the moment you got out of bed today to the point where you sat down to watch this video, you've essentially been swimming. Why? Because air is a fluid just like water. It has waves and eddies.
All right, air is a fluid. Just like water.
It flows, and when you push air out of the way, it rushes around you into a wake. so why don't we notice it most of the time? We commonly think of air as empty space. But while 1 cubic centimeter of interstellar space, the volume in the tip of your pinky finger, contains roughly 1 atom, the same volume of air has about 10 quintillion molecules. If that sounds hard to wrap your head around, it happens to be about the same as the number of insects alive on the planet, all crawling, climbing, and flying over each other in an enormous, tightly packed swarm. When this swarm of molecules runs into things, it exerts a force, pressing against the boundaries of the fluid like water pressing against the glass of a bottle. This is known as air pressure. And while air is
So, air pressure. The force exerted on an object by the air.
lighter than water, all those molecules still get pretty heavy, with the total air filling a typical school gym weighing about as much as an adult elephant. So when you walk into a gym, how come you're not immediately crushed by the elephant of air in the room? Well, first of all, because most of it is pressing on the floor and the walls, and the part that is pressing on you is pushed back by the pressure inside you.
All right? We don't feel air pressure because it pushes our body pressure pushes back. Hence we don't notice it.
You see, the air, as well as the water and everything else that fills our bodies, exerts an amount of pressure equal to that of the air outside. Of course, this is no accident. It's precisely what allows us to survive in the normal atmosphere, and what makes it more difficult at high altitudes or deep water. And we normally don't feel the air pressing on us because it's generally uniform. So even though different amounts of air molecules are hitting you at different times, the swarm is so thick that all those little differences average out. What happens when air pressure isn't uniform? This means that the molecules are pushing harder in one region of air than another, driving the airflow from the higher pressure region to the lower. We feel this flow directly as wind, and the pressure systems that meteorologists are always going on about are responsible for other weather changes.
All right, so wind is from pressure differences in the air. That's what wind is.
From the mundane to the catastrophic. But differences in air pressure do more than just let us complain about the weather. They're the very reason we're alive. We breathe by lowering the pressure in our lungs, allowing air to rush in. So the next time you take a deep breath, think of the unfathomable number of air molecules you're commanding to move.
All right, so when we breathe in, we lower pressure, and the lower pressure in our body makes air rush in.
We look up at the night sky to ponder the infinity of space. But unless you're watching this video from that deep space, there are more air molecules in and around your body than there are grains of sand in all the world's beaches and deserts, stars in the visible universe, or both of those numbers combined. The vastness of the universe is right in front of you and inside you.
All right, so all around us is air pressure. We don't feel it because our body is exerting the same pressure back, but it is pushing down on us and it is heavy. You got about the weight of an elephant on your shoulder. All right, and that ends evidence D. Okay, this is evidence E. We're going to discover evidence about a vacuum. A partial vacuum.
You may remember learning about vacuums in high school. Perfect vacuums are impossible, thanks to quantum fluctuations, fickle photons, and atoms. Partial vacuums, on the other hand, are everywhere.
Okay, so complete vacuums impossible. Partial vacuums impossible. So we're going to figure out what a partial vacuum is.
From outer space to inside a straw. They're created when air is pumped out of something. So how are these related to the thing in your house that's also called a vacuum? Thing in your house that's also called a vacuum. So how are these related to the thing in your house that's also called when air is pumped out of something?
Okay, so partial vacuums are possible. They are created when air is pumped out of something.
So how are these related to the thing in your house that's also called a vacuum? To answer that, you must first understand that vacuum cleaners don't suck. Instead, they create a partial vacuum, which pushes particles into the machine.
All right. Vacuum cleaner works not because it sucks, but because it pushes things in.
But not all vacuums are created equal. Ones with powerful lightweight motors let you clean your home quickly and efficiently. So why does a top-of-the-line vacuum like a Dyson work so well? The Dyson Cyclone V10 vacuum runs for up to an hour, cord-free and fade-free. It has better airflow and more suction power in a smaller package, capturing minuscule particles and expelling cleaner air than the air you breathe.
Okay, so that video was about a Dyson vacuum, but it did a pretty decent explanation explaining that vacuum cleaners work not because they suck, but because there's a fan. The fan is lowering the air pressure in the vacuum, and things are being pushed into the vacuum. Okay, now we'll watch this other perfect vacuum.
As an elementary school teacher, I am constantly writing. Something that has helped me pick up the pace, it is
The universe is bustling with matter and energy. Even in the vast apparent emptiness of intergalactic space, there's one hydrogen atom per cubic meter. That's not to mention a barrage of particles and electromagnetic radiation passing every which way from stars, galaxies, and into black holes. There's even radiation left over from the Big Bang. So, is there such thing as a total absence of everything? This isn't just a thought experiment. Empty spaces, or vacuums, are incredibly useful. Inside our homes, most vacuum cleaners work by using a fan to create a low-pressure, relatively empty area that sucks matter in to fill the void.
Okay, so let's add to this vacuum cleaner. A vacuum cleaner works not because it sucks, but because it pushes things in. And it does this by creating an area of lower pressure. You know what we forgot to write at the beginning? What is a vacuum? A vacuum is nothingness.
But that's far from empty. There's still plenty of matter bouncing around. Manufacturers rely on more thorough, sealed vacuums for all sorts of purposes. That includes vacuum-packed food that stays fresh longer, and the vacuums inside early light bulbs that protected filaments from degrading. These vacuums are generally created with some version of what a vacuum cleaner does, using high-powered pumps that create enough suction to remove as many stray atoms as possible. But the best of these industrial processes tends to leave hundreds of millions of atoms per cubic centimeter of space. That isn't empty enough for scientists who work on experiments like the Large Hadron Collider, where particle beams need to circulate at close to the speed of light for up to 10 hours without hitting any stray atoms. So how do they create a vacuum? The LHC's pipes are made of materials like stainless steel that don't release any of their own molecules and are lined with a special coating to absorb stray gases. Raising the temperature to 200 degrees Celsius burns off any moisture, and hundreds of vacuum pumps take 2 weeks to trap enough gas and debris out of the pipes for the collider's incredibly sensitive experiments. Even with all this, the Large Hadron Collider isn't a perfect vacuum. In the emptiest places, there are still about 100,000 particles per cubic centimeter. But let's say an experiment like that could somehow get every last atom out. There's still an unfathomably huge amount of radiation all around us that can pass right through the walls. Every second, about 50 muons from cosmic rays, 10 million neutrinos coming directly from the Big Bang, 30 million photons from the cosmic microwave background, and 300 trillion neutrinos from the sun pass through your body. It is possible to shield vacuum chambers with substances, including water, that absorb and deflect this radiation, except for neutrinos. Let's say you've somehow removed all of the atoms and blocked all of the radiation. Is the space now totally empty? Actually, no. All space is filled with what physicists call quantum fields. What we think of as subatomic particles, electrons and photons and their relatives, are actually vibrations in a quantum fabric that extends throughout the universe. And because of a physical law called the Heisenberg principle, these fields never stop oscillating, even without any particles to set off the ripples. They always have some minimum fluctuation, called a vacuum fluctuation. This means they have energy, a huge amount of it, because Einstein's equations tell us that mass and energy are equivalent. The quantum fluctuations in every cubic meter of space have an energy that corresponds to a mass of about 4 protons. In other words, the seemingly empty space inside your vacuum would actually weigh a small amount. Quantum fluctuations have existed since the earliest moments of the universe. In the moments after the Big Bang, as the universe expanded, they were amplified and stretched out to cosmic scales. Cosmologists believe that these original quantum fluctuations were the seeds of everything we see today, galaxies and the entire large-scale structure of the universe, as well as planets and solar systems. They're also the center of one of the greatest scientific mysteries of our time, because according to the current theories, the quantum fluctuations in the vacuum of space ought to have 120 orders of magnitude more energy than we observe. Solving the mystery of that missing energy may entirely rewrite our understanding of physics and the universe. If you enjoyed this lesson, please...
Okay, so let's try to draw how a vacuum works. All right, so we'll say here is the container we're trying to create a vacuum in. So you get a fan. That's one way to do it. And the fan pulls air out. When you pull air out, you're going to lower pressure inside the vessel, whatever that may be. A vacuum. Okay, when you lower the pressure inside the vessel, that means the surrounding air is going to just naturally have higher pressure. If you have low pressure in there, high pressure on the outside, things are going to naturally want to go into the container, things like dirt and debris, if you happen to be vacuuming something up. But if there's no dirt and debris, then just outside air will flow into the container if there's an opening. That is how your vacuum cleaner works. There's no such thing as suction. Suction is just what it appears to be, but it's actually two different pressures. And pressure always flows from an area of higher pressure to an area of lower pressure. We spoke earlier, that's what wind is. A lot of weather systems are because of movement from higher pressure to lower pressure. And there you go. That is evidence E.